Hi, welcome to my channel. In the previous videos, we discussed about the support vector machine classification techniques. Support vector machine classification techniques, it performs in two ways, for the linear data and the non-linear data. That is linear classification and the non-linear classification techniques. Okay, non-linear classification techniques. In this video, I am going to discuss about the support vector machine regression. So, the support vector machine algorithm is versatile. Not only does it support to the linear and non-linear classification, but it also supports the linear and non-linear regression. So here there are two types of techniques are there. One is classification and regression. In the supervised learning algorithm, in the supervised machine learning supervised learning algorithm, there are two things are there. One is classification and regression. Okay. The support vector machine perform the both classification as well as non-regression techniques. So here in the classification also there are two types of techniques are there. One is linear classification and non-linear classification. So both will perform with our support vector machine algorithm. So it's one of the best algorithm to perform the linear and non-linear classification as well as linear and non-linear regression techniques. Okay. So this is one of the best algorithm to perform the linear and non-linear classification as well as linear and non-linear regression techniques. Okay, so now to use the support vector machines for regression instead of classification, the trick is to use the reverse the object function of the classification. Okay, so instead of trying to fitting the largest possible state between the two classes while limiting the margin violations. In the classification techniques, for example, the positive class are there, and negative class are there. Okay, we are going to maximize the margin between these two classes. That is very important in the classification techniques. But okay, so here with the help of support vectors, we are going to separate the data points into two parts. Okay, so here we are going to use the one hyperplane. That hyperplane that exactly separate the data points into two parts. So here the margin is going to be very maximized. Okay, so that is the important concept in the classification techniques. So here this is called a margin maximization. That is the main important concept in the maximization in the classification techniques. But while support vector machine regression, it tries to fit as many as instances as possible on the state while limiting the margin violations. So that means in the classification techniques, so no instance does not present within the margins. But whereas coming to regression, we are going to violate the margin violations. Okay. So that means in more number of points are present between the margins. That is a major difference between the classification and the regression techniques. So the width of the street is controlled by the one hyperparameter. That hyperparameter is called as a epsilon. So with the help of epsilon, we are going to increase or decrease the margin space, and also we are going to include the more number of instances within the margin. That is the major requirement of the regression. Okay. So here we are going to use the two linear SVM regression models. So with the help of epsilon equal to 1.5 and epsilon equal to 0.5. That means the margin between the thick line and the support vectors is going to be very high here, and here is very less here. Okay, so that more number of instances present between these margins between the two margins, and here less number of instances are present between these two support vectors. Okay, so on some random linear data, one with the large margin with epsilon equal to 1.5 and one with the other small margin epsilon equal to 0.5. That means if the help of epsilon is very high here, okay, compared to less one. Okay, here it contains 1.5. That means here also it contains epsilon equal to 1.5. So that means the margin is going to be very high. So that more number of instances are between these two lines, these two hyperplanes or supervectors. Okay, so but here with the help of less margin space, we are getting the less number of instances between these two hyperplanes. And adding more training instances within the margin does not affect the model prediction. So thus the model is said to be epsilon insensitive. Okay, you cannot use the scikit-learn linear SVM classification regression. Linear support vector machine regression class to perform the linear support vector machine regression. Okay, so here we are going to see the one code that produces the model represented on the left side of the figure with the figure and okay. So with the help of epsilon equal to 1.5 and the epsilon equal to 0.5. So from the sklearn dot svm import to linear SVR. We are importing the linear SVR, linear support vector machine regression. Okay, the SVM regression equal to linear SVR epsilon equal to 1.5. The epsilon equal to 1.5. With the help of this one, we are going to train the model. Okay, that means the SVM underscore regression dot fit of x comma y. X is nothing but your features and y nothing but your class labels or corresponding values. Now, to tackle the nonlinear regression task, we are using the kernelized SVM model. But whereas the linear model, we are simply using the linear SVR classification with epsilon equal to 1.5 or epsilon equal to 0.5. This is for the small margin and this is for the high margin. For this, we are having the more number of instances present between these two support vectors. Here, less number of instances present between these two support vectors. Okay, but if you want to confirm the nonlinear fashion, so we are going to use the concept called as a kernelized SVM models. So here we are going to see the two diagrams that represents the SVM regression model and the random quadratic training set. Using the second degree polynomial kernel. So here the degree equal to 2 and the support c equal to 100 and the epsilon equal to 0.5. So and this is also here the degree equal to c equal to 0.001 and the epsilon equal to 0.1. Here in the both the cases epsilon equal to 0.1 and the c equal to here is 100 and here equal to 0.001. That means here more number of instances are present between these two support vectors and less number of instances present between these two support vectors. Okay, so there is a little regularization in the left plot, that is a large c value, and on the right side much more regularization in the right plot. Okay, it is small c value. So this is the difference between with the c value with the different values. C equal to 100 and c equal to 0.1. Okay. Now here we are going to see the scikit-learn code with the help of SVR classification. Okay, SVR regression. So it supports the kernel trick to produce a model. Okay, so here from sklearn.svm you are importing the support vector regression. So our model is a support vector regression. It is a non-linear fashion. Okay, so support vector machine polynomial degree. Okay, polynomial regression equal to SVR kernel equal to poly degree equal to 2 c equal to 100 and epsilon equal to 0.1. So that means we are going to use the kernel as a polynomial kernel and degree equal to 2 and c equal to 100 and epsilon equal to 0.1. So support vector machine polynomial regression dot fit function, we are providing the x and the corresponding y. So these are the data we are going to provide for the based on this data set we are going to train our model. So after that we are going to predict the class labels. Regression values are like that lies on the thick line. Okay, that is the model performance. Okay, now SVR class is the regression equivalent to the SVC class. There are two things are there in the support vector machine. One is SVR support vector regression class and support vector classification class. Okay, the linear SVR class is the regression equivalent to the linear SVC class. So linear SVR is equivalent to the linear SVC class. Okay. Now linear SVR class is scales the linearly with the size of the training set. okay, like a linear SVC class. So while the SVR class gets the much too slow, then the training set is grows large. So that's like a SVC class. So this is about the support vector machine regression. Okay, SVM can also be used to find out the outlier detection. Okay, so this is about the support vector regression. Thank you for watching our video. If you like the video, please subscribe my channel. Thank you.